This is Mario 64's random function. It's elegant, relatively small, and has some cool math, but it is also flawed. It can generate 65,534 out of the 65,536 possible 16-bit values, and does so by taking the last number it spat out, doing some random looking math on it, and spitting out a new number. This approach has 3 issues, but I came up with a new function that solves all 3 of them, and even includes true randomness, something computers seriously struggle with, through a complete accident that just so happens to work out in my favor, and I kind of hate it. But before that, we need to talk about why I even want a new algorithm in the first place, and also give a shout out to Squarespace for being this video's sponsor. The first of the 3 issues is by far the most important to me. All this math just to generate one single random number is an unreasonable amount of CPU cycles and too much data throughput for what it does. The second issue is that the vanilla RNG's output is not true randomness. It is sequential and predictable. Each number is going to appear exactly once before a number can repeat. It takes the previously generated number and generates a new one based off of that, which means if you know the current state, you know exactly what the next number will be, and the one after that, and so on. Arguably, this is not an issue, but rather an upside. After all, that predictability leads to some really cool tricks. If you've ever seen a video by Pan and Coke 2012, you've already witnessed how players can manipulate the RNG by spawning dust clouds or coins at just the right time to push the seed into the desired state. This works because randomness in Mario 64 is used for things such as dust particles, coin spawn velocities and directions, and some enemy decisions, allowing players to execute RNG manipulation. And this lets them, for example, figure out the pendulum on the random setting a TikTok clock. I do like that it is possible, but saying that it is not a bug that Pan and Coke can get the pendulum to spin for 40 days until it gets so fast that the game crashes is a bit of a stretch in my opinion. The third issue is more of a nitpick, but I'd still like it fixed. The RNG output doesn't cover every possible output. Out of the 65,536 possible 16-bit values, 2 stay unreachable, which skews probability just a little bit. The bit 0 probability being off by 0.0015% is not a big deal, but if you're rewriting this anyway, why not go all the way and unlock everything? If we're going to replace Mario 64's RNG, it is important that our replacement function does not noticeably affect any of vanilla Mario 64's functionality. Keeping that in mind, the simplest, cheaper replacement for Mario 64's RNG function would be a lookup table that simply cycles the random values. My first approach was to simply pre-compute the random table and store a list of all random values sequentially, and instead of doing all this math on the seed, we just increase the seed by 1. This keeps perfect vanilla RNG parity, while except as a little bonus, I'll even throw in the 2 unreachable RNG values from the previous function. This turns the whole random function into a much faster 7 assembly instructions and 2 memory accesses. 1 access for the seed and 1 for the random table, down from 84 instructions and 1 memory access of the original function. Of course, this means we would store 65,536 pre-computed 2-byte values in memory, and that costs just over 3% of the Nintendo 64's total RAM. But to be honest, with the expansion pack, you have practically unlimited memory on this console anyway, so I don't see this as too big of an issue. I already have 1 whole megabyte large memory bank just dedicated to the Z buffer, so I can chuck it right next to that and not lose any usable memory. The Z buffer has so much empty space next to it for weird and complicated performance reasons, but considering how rarely RNG is read, accessing this bank a handful of times a frame shouldn't be showing up in any performance graphs. But this obviously kind of sucks. It technically works, but it is not very portable because not every game has that much memory left over, and to be honest, it does feel cheap and uninspired. Surely there's a better option. If you are familiar with pseudo-RNG algorithms, your first instinct may have been a XOR shift style algorithm. XOR shift takes a seed and only does these 6 operations here to output a new value, which then gets stored back as the seed, just like the vanilla RNG. In total, this would be 9 instructions and 1 memory access, which is arguably better than the 7 instructions and 2 memory accesses from the previous function. This algorithm actually reaches 65,535 of the 65,535 36 16-bit values. And the values apparently feel random enough, and the only value it can generate is 0. You could argue that this is a strictly superior algorithm. Interestingly, this algorithm apparently was only invented as recently as 2003, so this couldn't have been made into an N64 game. Despite that, the people designing the N64 hardware actually gave us the tools to build something much more random than that. Via its coprocessor 0, that's also much faster than this and does not require a RAM access. The N64 hardware has 2 relevant special registers that you can only address using machine code or a custom operating system: the random register and the count register. A register is a special hardware part that is built directly into the electrical circuits of the machine. This means they can be read without accessing memory. Registers also often have functionalities that are not handled in software, but rather by background processes happening while the console is powered on. Now you may think, oh, there's a random register, problem solved, we'll just read that. But hold on, it is the random register in name only. All it really does is count down by 1 after each instruction from 31 to 0, resetting back to 31 whenever it reaches 0. The count register is much more interesting though. The count register keeps track of how many CPU cycles have passed since the console booted. That practically just tracks time, but CPU cycles are very volatile. If you read memory, you may get a cycle penalty around 50 cycles in the best case, but look at my instruction cache miss cycle test here. Compare doing it in a cheap area, where it usually takes 46 cycles, to doing it in an expensive to render area, where it will often take hundreds of cycles. Because the RAM bus is busy moving render data around, it can't make time to load the code. Also, at any point during the game's runtime, a thread switch could occur that will add literally hundreds or thousands of cycles. With the N64 having 93.75 million cycles per second, at 60 FPS, that's 1.5 million cycles per frame, which is about 24 times as many cycles as there are 16-bit numbers. That means that just reading the lower 16 bits of the count register would already give you a decent randomness, assuming you rarely use this function. But it is not perfect. Using this random function twice in short succession would have the results be strongly correlated. After all, if your code were to look like this, the most likely outcome is that only a handful of cycles passed since the last random call. To somewhat mitigate this, I'll left shift the random register by 11, turning its number from 0 to 31 into a number between 0 and 63,488, hex 0xF800, and then XOR the count register onto it. This adds some much needed quick variation to the higher bits of the output, and since these are CPU registers, that means we can run the random function entirely without accessing memory. And it only costs us 5 cycles too, cheaper than the lookup table or the XOR shift. I am very happy with this one. It's fast and very random, but there are some drawbacks that I don't enjoy. First, the strong correlation between 2 subsequent RNG calls is still there. This makes it entirely unsuitable for a general purpose repository everyone is supposed to use, but we in the know can work around this. The second is, well, look at this idle animation picker. It picks a random idle animation when Mario finishes previous one. I reset the console and his first special animation is looking around. I reset the console again and now he's adjusting his glove. When using cycle counts, the actual physics of the hardware that we run this code on matter. I believe that even something like the temperature of your room may affect this. It's cool, but I don't like it. Of course, this is invisible in normal gameplay, but it makes tool-assisted speedruns with the current emulator impossible. And I do enjoy watching those and want people to make those. So how do we work around these two? The first can be solved by combining it partially with a XOR shift. Whenever we need 2 random values in a row, we could simply feed the output of this random function as a XOR shift seed into the XOR shift function and take advantage of XOR shift's randomness without requiring XOR shift's usual memory read and store back. This eliminates any correlation between 2 subsequent calls, and additionally, XOR shift's algorithm, without having to read or store back the seed, is 2 instructions cheaper than usual, meaning this gives us all the randomness of the XOR shift algorithm, basically no extra cost and near perfect randomness. But honestly, so far that type of situation is very rare. The truth of the matter is that we barely ever need 2 random calls in a row, and even when we do need 2 random calls in a row, the randomness rarely matters beyond visuals where a correlation wouldn't be visible. Random calls just aren't happening often enough in Mario 64, or even if they do happen, it doesn't really matter if the results are somewhat correlated. But the fact that the code is now non-deterministic deterministic is much harder to solve, and honestly, I'll put that responsibility onto emulator programmers. My favorite emulator, the yet to be released version of NEMU64, seems to already handle this in a consistent manner. But the count register is chaotic, and no other emulator I've tried, and not even a real Nintendo 64, can execute this code in a consistent way. Either way, that will be for someone else to figure out. Maybe in the future, we'll have an emulator with options emulating your room's temperature, moisture, and astral ray exposure. So, now we have a super fast RNG, but before we can finalize this as our new RNG algorithm, we need to prove that this algorithm really is random enough. When I first showed this on my second channel, a ton of people doubted that this would produce random outputs for some reason. To prove that it does, we can take a look at some RNG evaluation tests that can rate the randomness of a bit stream through a series of mathematical tests. I found a decent one online by just typing RNG test online into Google. Let's check 512 randomly generated bits. This website has presets for radioactive decay, the ADV noise, and then JavaScript pseudo RNG for us ready to compare to. All the presets passed 6 of these tests when 512 bits were pre-generated, an error on all of the other tests, probably due to the input numbers being too small. Just like all the presets, my algorithm also passed 6 tests. Good sign, but I need more proof. Fortunately, every other method of checking I've tried also said my output is random enough. Now I know that ChatGPT is a horribly unreliable source of information and is not to be trusted, but if you tell it to run its Python API, it actually most of the time produces output grounded in reality. Since instead of hallucinating together language, it will just stitch code snippets from online together and show you their output. Basically, it just saves you a ton of Googling. So I ordered ChatGPT to stitch together Python scripts for commonly used RNG tests online to check if everything was fine. And we passed the bit balance, the runs test, the repeating pattern tests, and the entropy estimate. I've also had it find and run Python scripts for the frequency monobit, the serial test, the chi-square test, and an approximate entropy test. Full disclosure, I barely know what these are, but they are common algorithms to check if random patterns are random enough. And I passed all of them with flying colors. Obviously, I still have no proof that the Python scripts it ran are mathematically sound, but if we pass every human design test and every test the AI could find, I think that is solid evidence that this is random. So after that, I did what any reasonable person would do and had my N64 run for an entire night to generate random bits using my algorithm to verify the results are uniform enough. I had it write to a color output buffer that I would then render to the screen. Since Mario 64 outputs 320 by 240 pixels, so 76,800 pixels, which is more than 65,536, we can simply run the RNG algorithm once a frame to pick one of the first 65,536 pixels and increase the blue channel of that pixel by 1. This is the output after running it overnight, and I do not see any patterns in here at all. If anyone sees patterns, let me know, but I'm pretty sure we can say that this is random and uniform enough. That means this algorithm is more than good enough. So, with all this, what is the verdict? How much performance did we save? Let's benchmark all 3 random functions. Since these are all relatively fast, let's scale it up and run each one 65,536 times in a row. This is actually the best case scenario for both the lookup table and the original random function, because their greatest weakness was that they took so much data throughput, and calling them multiple times in a row means that most of the data is already hot in cache. So what are the results? 65,536 calls of vanilla RNG cost us 23.1 milliseconds. 65,536 calls of the lot RNG cost us 6.4 milliseconds, but 65,536 calls of the new hardware RNG only cost us 2.8 milliseconds. What an improvement. About 8 times faster than the vanilla algorithm and twice as fast as a lookup table. And remember, this was the comparison that favored the vanilla function the most. In real-world scenarios, the speed multiplier is going to be much higher. Calling any of these just once will cost less than a handful of microseconds, which remember is just the thousandth of a millisecond, which unfortunately is too small to measure. But let's do a quick estimate of what one call will cost in theory just by doing some math. One call of vanilla RNG actually takes 84 instructions and one data access, which would take around 2.2 microseconds of data throughput to execute. Quite expensive. One call of lookup table RNG takes 7 instructions and 2 memory reads. 7 instructions cost about 0.175 microseconds and 2 memory reads should cost about 0.2 microseconds. So about 0.375 microseconds in total. One call of hardware RNG only costs us 5 instructions with no memory reads. So just about 0.125 microseconds in total. It is almost 3 times as fast as the LUT and about 17 times faster than the original algorithm. But that is not even the best part. One cool advantage here that I did not even mention yet is that this new function is actually so small that we can always inline it without blowing up the memory. In fact, inlining it reduces the code's memory footprint because it being inlined means functions don't have to back up registers before running it. And you know what else I didn't even mention yet? The entire 128 kilobyte lookup table that the previous function had is no longer required. So not only did we save performance, we also introduced true randomness and saved a bunch of memory. And how many FPS did we gain from this? Unfortunately, basically none. Going from spending 2 microseconds a frame to spending 0.4 microseconds a frame on RNG is not going to have a measurable performance impact. Still, I don't think this has ever existed before in a Nintendo 64 game, and that is extremely cool. Let me know what you think. Shoutouts to Squarespace for sponsoring this video. Squarespace gives you all the tools you need to offer services or get paid with your own customizable website. Streamline your workflow with built-in appointment scheduling and professional on-brand invoices. Squarespace makes it easy to make your own website and go online. They even help you buy a domain without any hidden fees. Plus, they have privacy and security tools to help your website stay online. They also offer design tools so anyone can build a decent website. They have customizable templates for you and you can edit everything via simple drag and drops. Go to squarespace.com for a free trial, and when you're ready to launch, go to squarespace.com/Kaze Emanuar to save 10% of the purchase of your first website or domain. Shoutouts to all my Patreons for supporting the channel. You guys are the reason I make these videos. This background footage here is from the game I am working on that uses all these performance improvements and new tech. I've decided that all Patreons will be listed in the game's end credits as donors. Once that game is done, I'll also open source it and you guys can use it all as a base for your Nintendo 64 games.